This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome to the incredible journey of camel evolution. In this exploration, we'll unravel the fascinating story of these remarkable creatures, from their surprising origins to their incredible adaptations for survival in some of the harshest environments on Earth. We'll use clear, easy-to-understand language to delve into the rich history of the camelid family, a group of even-toed ungulates whose lineage spans continents and millions of years. Prepare to be amazed as we trace the camel family tree, uncovering its unexpected beginnings in North America and following its branches as they spread across the globe. We'll meet the diverse members of this family, from the iconic one-humped dromedary and two-humped Bactrian camel of the Old World deserts to the smaller, fleece-covered llamas, alpacas, guanacos, and vicuñas of the South American Andes. We'll explore their unique characteristics and discover how each species has carved its own niche in the world. This journey will take us through dramatic climate changes, across ancient land bridges, and into the heart of the camel's incredible adaptations. We'll uncover the secrets of their remarkable resilience, exploring how they thrive in environments of extreme heat and cold, from scorching deserts to frigid Arctic landscapes. We'll delve into the fascinating details of their physiology and behavior, discovering how their humps, specialized feet, efficient kidneys, and unique blood composition all contribute to their survival in a world of extremes. Get ready to uncover the lost history of North American camels, tracing their rise and fall and exploring the mysteries surrounding their extinction. We'll journey to the high Arctic, uncovering fossil evidence that rewrites the camel's evolutionary narrative. We'll examine the pivotal role of migration in shaping the camelid family, tracing their dispersal across continents and the subsequent diversification that led to the remarkable variety we see today. By the end of this exploration, you'll have a deeper understanding of the camel's remarkable journey through time. You'll appreciate the intricate interplay between evolution and environment, and you'll marvel at the ingenuity of nature's adaptations. Join us as we uncover the secrets of the camel, a true testament to the power of life to thrive in a world of extremes. Chapter 1. A Family Reunion. Unraveling the Camelid Family Tree. Welcome to the captivating story of the camelid family, a remarkable group of even-toed ungulates whose evolutionary journey spans continents and millions of years. From the familiar, humped figures silhouetted against desert sunsets to the more diminutive, fleece-covered camelids of the Andes Mountains, this family's history is a testament to adaptation and survival. Join us as we unravel the branches of their family tree, tracing their lineage back to an unexpected origin and exploring the remarkable transformations that have shaped the camels and their relatives we know today. The camelid family comprises 7 distinct species, each with its own unique characteristics and story. Let's start with the true camels, the iconic desert dwellers. The dromedary or Arabian camel, with its single majestic hump, is the most numerous, representing 94% of the world's camel population. These resilient creatures are found across the Middle East, the Sahara Desert, and South Asia, and have even been introduced to Australia. Then there's the Bactrian camel, easily identifiable by its 2 humps. Domesticated Bactrian camels comprise about 6% of the world's camel population and are primarily found in Central Asia, including the historical region of Bactria and Turkey. A close relative, the wild Bactrian camel, is tragically on the brink of extinction. Fewer than 1,000 of these magnificent animals remain, clinging to survival in the remote deserts of northwest China and Mongolia. Though similar in appearance to their domesticated cousins, wild Bactrian camels are genetically distinct, representing a separate species altogether. Venturing across the globe, we encounter the New World camelids of South America. These smaller, hump-less relatives share the camelid lineage but have carved their own niches in the diverse ecosystems of the Andes. The llama, the largest of the South American camelids, has been domesticated for centuries, serving as a pack animal and a source of wool, meat, and hides. Alpacas, closely related to llamas, are also domesticated and prized for their exceptionally soft fleece. Their wild cousins, the guanaco and vicuña, roam the high-altitude plains and mountains, exhibiting an elegance and resilience all their own. Guanacos, larger and more robust, are known for their reddish-brown coats and social behavior. Vicuñas, the smallest of the camelids, possess a delicate, cinnamon-colored fleece that is among the finest and most expensive in the world. The story of these diverse creatures, however, doesn't begin in the deserts of Asia, Africa, or the high Andes. It begins much further north, in a place that might surprise you: North America. Imagine, if you will, North America during the Eocene epoch, some 40 to 45 million years ago. A world far different from the one we know today. This was the birthplace of the camelid family, a time when their ancestors, small and unassuming, first emerged. Fossil evidence reveals a fascinating array of extinct North American camelids, painting a picture of a family undergoing rapid diversification and adaptation. Among these ancient camelids were species like Camelus gratardi and Camelus knoblochi, along with Camelus morelli and Camelus civalensis, and Camelus thomasi. These names, though unfamiliar, represent important stepping stones in the camel's evolutionary journey. Their fossilized remains provide clues to the gradual changes in size, limb structure, and dentition that would eventually equip their descendants for life in more challenging environments. These early camelids were not desert specialists. They roamed a North America covered in lush forests and grasslands, far different from the arid landscapes we associate with camels today. As the climate changed and grasslands expanded, camelids evolved, growing larger and developing features suited to grazing. Around 6 million years ago, a pivotal moment in camelid history occurred. A species known as Paracamelus, considered the ancestor of modern camels, embarked on a remarkable journey, migrating westward across the Bering Land Bridge, a then exposed pathway connecting North America and Asia. This migration marked the beginning of the camelid's expansion into the Old World. Some Paracamelus populations ventured even further, eventually reaching Africa. Meanwhile, back in North America, other camelid lineages continued to evolve, adapting to the changing conditions of the continent. The divergence of camelid lineages across continents set the stage for the remarkable diversity we see today. The Paracamelus descendants that migrated to Asia and Africa would eventually give rise to the dromedary and Bactrian camels, masters of desert survival. Those that remained in North America would diversify further, with some lineages eventually migrating south, across the newly formed Isthmus of Panama, into South America. These South American migrants became the ancestors of the llamas, alpacas, guanacos, and vicuñas, each uniquely adapted to the varied landscapes of their new home, from high-altitude plains to rugged mountain slopes. The North American camelids, however, met a tragic fate. Despite their long and successful reign on the continent, they vanished around 13,000 years ago, victims of the dramatic climate shifts and extinctions that marked the end of the last ice age. Their story, though lost to time, is an essential piece of the camelid puzzle, providing context for the remarkable adaptations of their surviving relatives. The stage is now set for a deeper exploration of the incredible adaptations that have allowed camels to conquer some of the harshest environments on Earth. Join us in the next chapter as we delve into the specifics of these evolutionary marvels, uncovering the secrets of their remarkable ability to thrive in a world of extremes. Chapter 2. Lost Camels of the Arctic: A Journey to Ellesmere Island. The familiar image of a camel, silhouetted against the fiery backdrop of a desert sunset, has long been synonymous with resilience in the face of harsh, arid conditions. But what if I told you that this iconic desert dweller has roots in a place far removed from scorching sands and endless dunes? What if I told you the camel's story begins not in the Old World, but in the frigid expanse of the high Arctic? Journey with me to Ellesmere Island, the northernmost island in the Canadian Arctic archipelago, a land of stark beauty and unforgiving extremes. Here, amidst the scattered remnants of ancient forests, lies a secret that has rewritten the evolutionary history of the camel. It's a story of adaptation, migration, and ultimately, extinction, a story etched in the very rocks and fossils of this remote, icy landscape. Picture Ellesmere Island during the mid-Pliocene warm period, roughly 3.4 million years ago. The world was experiencing a period of elevated temperatures, and even the high Arctic felt the warmth. While not tropical, the Arctic was significantly warmer than today, with mean annual temperatures estimated to be about 18 degrees Celsius higher. Imagine lush boreal forests, similar to those found much further south today, teeming with life. Wetlands dotted the landscape, providing habitat for a diverse array of plants and animals. Beavers busily constructed their dams, and the telltale signs of seasonal freeze-thaw cycles, known as ice wedge casts, marked the landscape. This was the unexpected home of the high Arctic camel. The discovery of these camels began not in a sterile laboratory, but in the gritty reality of an active placer gold mine along Hunker Creek, near Dawson City, Yukon. Here, amidst the clamor of heavy machinery and the rush for gold, paleontologists stumbled upon a treasure trove of Pleistocene fossils. The hydraulic stripping of frozen sediments, a necessary process for accessing the gold-bearing gravels below, often unearthed these ancient remnants, providing a window into a lost world. Among these fossils were fragments of leg bones, initially unremarkable, perhaps even overlooked. But closer examination revealed their unique camelid morphology, the telltale characteristics of the camel family. However, these fossils were not found in the neatly layered strata that geologists dream of. The non-stratigraphic nature of placer mining meant that precise dating was a challenge. The associated fauna, including steppe bison, suggested a late Pleistocene age, possibly within the Sangamonian interglacial period, between 130,000 and 75,000 years ago. Radiocarbon dating of the camel specimens themselves yielded inconclusive results, further complicating the puzzle. To determine the age of these intriguing fossils, scientists turned to a sophisticated technique known as terrestrial cosmogenic nuclide burial dating. This method relies on the analysis of isotopes like aluminum-26 and beryllium-10, which are produced in quartz when exposed to cosmic rays. Once buried, the ratio of these isotopes changes as they decay at different rates. By measuring these ratios, scientists can determine how long the quartz has been buried, providing an estimate of the fossil's age. The results were astounding. The fossils were determined to be older than 3.4 million years old, placing them squarely in the mid-Pliocene. But the age of the fossils was only part of the mystery. The fragmented nature of the bones made traditional identification methods difficult. Scientists needed a way to confirm that these bones belonged to a camel, and to determine their relationship to other camel species. They turned to a cutting-edge technique called collagen fingerprinting. Collagen, the dominant protein in bone, can persist for millions of years, even after DNA has degraded. By extracting tiny amounts of collagen from the fossils and analyzing the unique peptide sequences, scientists created a collagen profile. This profile was then compared to those of modern camels and other mammals. The results were unmistakable. The Ellesmere Island fossils belonged to a member of the Camelini tribe, closely related to modern-day camels, particularly the dromedary. This discovery was a bombshell. Camels, the quintessential desert animals, had an ancestor living in the high Arctic, a forested environment far removed from the arid landscapes we associate with them today. The implications were profound. This high Arctic camel forced a re-evaluation of camel origins and suggested that some of the camel's most iconic adaptations might have evolved not for desert survival, but for life in a colder, more challenging environment. The fossil material itself, consisting of fragments of a tibia or lower leg bone, provided further clues. The size of the fragments indicated a large animal, possibly even larger than modern dromedaries. But more importantly, the collagen profile linked it definitively to the camel lineage. This wasn't just any Arctic mammal. This was a camel, thriving in a world of forests, wetlands, and prolonged periods of darkness. Consider the challenges faced by this high Arctic camel. Long, cold winters with limited food availability would have necessitated efficient energy storage. Navigating snowy or soft ground would have required specialized feet. And extended periods of darkness might have favored the development of large, sensitive eyes. These very challenges may have driven the evolution of some of the camel's most distinctive features. The hump, so often associated with water storage, a misconception, actually serves as a reservoir of fat. This fat, accumulated during times of plenty, provides a crucial energy source during lean winter months. The camel's wide, flat feet, perfect for traversing desert sands, might have originally evolved for navigating snow and soft ground. And the large eyes, so effective at filtering out blowing sand, might have initially developed to enhance vision during the long Arctic nights. The discovery of the high Arctic camel not only rearranges the branches of the camelid family tree but also highlights the dynamic nature of our planet's history. The Arctic, so often perceived as a static, icy wasteland, has experienced periods of warmth and abundant life, supporting ecosystems far different from those we see today. And the camel, that enduring symbol of desert resilience, carries within its very being the legacy of a surprising Arctic ancestry. The story of the high Arctic camel is a reminder that evolution is a journey, not a destination, and that even the most familiar creatures can harbor unexpected secrets in their past. Chapter 3. The Camel's North American Roots and Desert Transformations. The camel's evolutionary narrative is a saga of remarkable adaptation, a transition from the verdant forests of North America to the arid deserts of Asia and Africa. Their journey began not amidst shimmering sands, but in the Eocene epoch, approximately 50 million years ago, in the lush forests of what is now North America. Their earliest ancestors, like Protolopus, were diminutive creatures, no larger than a rabbit, browsing on the abundant foliage. Protolopus possessed shorter front limbs, a characteristic that facilitated their foraging habits among the low-lying vegetation of their forest home. As the Eocene epoch gave way to the Oligocene, the North American climate began to shift. Forests receded, and vast grasslands expanded across the landscape. This environmental transformation exerted selective pressure on the camel lineage, favoring those individuals with adaptations suited to the new, open terrain. Camelids like Pobrotherium emerged, larger than their Protolopus predecessors, with longer legs and modified teeth designed for grazing on grasses rather than browsing on leaves. This marked a crucial step in the camel's evolutionary journey, a shift towards the physical characteristics we associate with their modern forms. The transition to desert life, however, required even more dramatic adaptations, a suite of physiological and behavioral modifications that would transform the camel into the ultimate desert survivor. This transition occurred gradually, over millions of years, as the camel lineage continued to diversify and adapt to increasingly arid environments. One of the most iconic camel adaptations is the hump, a unique fat storage unit located on their back. Contrary to popular belief, the hump does not store water directly. Instead, it serves as a concentrated energy reserve. The fat stored in the hump can be broken down to provide both energy and metabolic water, a byproduct of fat metabolism. This allows camels to survive for extended periods without food, a crucial adaptation in the resource-scarce desert environment. Dromedaries, with their single hump, can store up to 80 pounds of fat, while Bactrian camels, with their two humps, can store even more. When food is scarce, the hump gradually shrinks, becoming flaccid and drooping as the fat reserves are depleted. The camel's kidneys also underwent significant modifications, evolving into highly efficient water conservation organs. Camels can tolerate remarkable levels of dehydration, losing up to 25 to 30% of their body weight in water, a feat that would prove fatal for most other mammals. Their kidneys concentrate urine to a thick, syrupy consistency, minimizing water loss through excretion. Even their feces are remarkably dry, so dry, in fact, that they can be used as fuel for fires. This ability to conserve water is essential for survival in the desert, where water sources are often few and far between. Another remarkable adaptation lies within the camel's very blood. Their red blood cells, unlike the circular cells of most mammals, are oval-shaped. This unique morphology allows for efficient blood flow even during periods of dehydration, when blood volume decreases. Furthermore, camel red blood cells can tolerate significant fluctuations in water intake. They can swell to accommodate large influxes of water, such as after a camel drinks copious amounts following a period of dehydration, without rupturing. This flexibility is crucial for their survival, allowing them to rehydrate rapidly when water becomes available, absorbing over 100 liters in just 5 to 10 minutes. The camel's thick coat, while seemingly counterintuitive in a hot desert environment, plays a crucial role in thermoregulation. The coat acts as insulation, reducing heat gain from the scorching desert sun and minimizing the need for sweating. In fact, camels can tolerate an increase in body temperature of up to 6 degrees Celsius before they begin to sweat. This delayed onset of sweating further conserves water, a precious resource in the desert. Their coat also provides protection from the intense ultraviolet radiation of the desert sun and helps to regulate body temperature during cooler desert nights. Even the camel's head exhibits adaptations for desert life. Long eyelashes and bushy eyebrows shield their large, sensitive eyes from blowing sand and dust, while their closable nostrils prevent the entry of these irritating particles into their respiratory system. These features, along with a translucent third eyelid called a nictitating membrane, which acts like a windscreen wiper to clear any debris that does enter the eye, ensure that camels can navigate the desert landscape without compromising their vision. The camel's feet, too, are specialized for their desert habitat. Wide, flat, and padded, these feet distribute the camel's weight evenly, preventing them from sinking into the soft sand. This adaptation, along with their unique pacing gait, in which both legs on one side move together, allows them to traverse the shifting sands with ease and efficiency. Dromedaries, in particular, have a soft, wide-spreading pad on their feet that is specifically adapted for walking on sand, while Bactrian camels have a firmer foot better suited to the rocky terrains of Central Asia. Dietary adaptations have also played a key role in the camel's desert success. The limited vegetation of the desert necessitates the ability to consume tough, thorny plants that other animals would avoid. Camels have a thick, leathery lining inside their mouths, protecting them from the sharp thorns of desert plants. Their split upper lip, with two independently movable sections, allows them to graze close to the ground, maximizing their intake of sparse vegetation. Inside their mouths, firm, fleshy protrusions called papillae help them manipulate and swallow thorny food without injury. Like true ruminants, camels also chew cud, regurgitating partially digested food and chewing it again to further break down the tough plant fibers. While camels have a rumen where microbial fermentation occurs, they differ from true ruminants in having a 3-compartment stomach instead of 4, making them pseudoruminants. Behavioral adaptations also contribute to the camel's desert resilience. Their pacing gait, in addition to aiding locomotion on sand, minimizes energy expenditure during long journeys. Their ability to tolerate fluctuations in body temperature, as well as their efficient water conservation mechanisms, allows them to withstand the extreme heat of the desert day and the cooler temperatures of the desert night. Camels are also known for their remarkable ability to go without water for extended periods, surviving for 4 to 7 days in extreme heat and up to 10 months if the forage contains sufficient moisture. The camel's evolutionary journey is a testament to the power of adaptation. From their humble beginnings as small, forest-dwelling creatures, they have transformed into iconic symbols of desert survival. Their unique adaptations, honed over millions of years, have allowed them to conquer some of the harshest environments on Earth, a testament to the remarkable resilience and adaptability of life itself. Chapter 4. The Rise and Fall of Camelops, an American Camel's Tale. The western camel, Camelops hesternus, was a North American giant, the largest camelid of the Pleistocene epoch. Until its extinction approximately 13,000 years ago, Camelops stood as a testament to the unique evolutionary path of camels in North America. Unlike its modern-day relatives in the deserts of Asia and Africa, and its smaller cousins, the llamas and alpacas of South America, Camelops carved its niche across a wide swath of North America, adapting to diverse environments from the balmy subtropics to the frigid Arctic. Its story, etched in the fossil record, is one of remarkable success and ultimate tragedy, a poignant reminder of the constant flux of life on Earth. Camelops was a formidable creature, dwarfing even the largest modern-day camels. A full-grown adult could reach heights of over 2 meters at the shoulder, and with its hump or humps, a question still debated among scientists, it may have towered even higher. Its weight varied considerably, ranging from a substantial 300 kilograms to a massive 1,000 kilograms, reflecting the diverse environments it inhabited and the varying availability of food resources. Unlike the sleek, sandy hues of its old-world counterparts, the coat of Camelops is thought to have been a darker shade, perhaps providing better camouflage in the varied landscapes it called home. Camelops's adaptability is perhaps its most defining characteristic. This wasn't just a creature of the grasslands, though it certainly grazed on the abundant grasses of the North American plains. Its fossilized remains have been discovered in a surprising range of habitats, from woodlands to the harsh conditions of the Arctic. One particularly significant site is Hunker Creek in the Yukon, a region that, during the Pleistocene, experienced dramatic shifts in climate. Here, amidst the gold-bearing gravels, paleontologists have unearthed not only the bones of woolly mammoths and steppe bison, but also the telltale remains of camelops, suggesting its ability to tolerate conditions far colder than those experienced by its modern relatives. This adaptability was further enhanced by its unique physical characteristics. Its long, powerful legs weren't just for show, they provided an efficient gait, allowing it to cover long distances in search of food and water. The wide-spreading toes, terminating not in hooves but in broad, padded feet, provided stability and prevented it from sinking into soft substrates, whether snow, sand, or the muddy banks of ancient waterways. These feet, so effective in navigating varying terrains, are a testament to the evolutionary pressures that shaped camelops for life in a dynamic environment. The diet of camelops was as varied as the habitats it occupied. While grasses formed a significant part of its diet, it also consumed a diverse array of plants, leaves, and shrubs, adapting its foraging strategy to the available resources. In the more temperate regions, it likely grazed on leafy vegetation and shrubs, while in the Arctic, it may have browsed on the tougher, more fibrous plants that could withstand the harsh conditions. This dietary flexibility was essential for its survival, allowing it to thrive in environments where food sources fluctuated with the seasons. The extinction of camelops, however, remains a puzzle, a mystery shrouded in the mists of time. While human hunting undoubtedly played a role, as evidenced by butchered camelops bones found at some early human settlements, it's unlikely to be the sole cause of its demise. The end of the Pleistocene epoch was a tumultuous period, marked by dramatic climate change. As glaciers retreated and temperatures rose, the environments that camelops had adapted to began to shift, perhaps too quickly for it to keep pace. Competition from other species, both newly arrived and those expanding their ranges in response to the changing climate, may have also contributed to its decline. The disappearance of camelops was not an isolated incident. It was part of a larger wave of extinctions that swept across North America at the end of the Pleistocene, wiping out many of the continent's megafauna, including mammoths, mastodons, and saber-toothed cats. This megafaunal extinction event remains a topic of intense debate among scientists, with various theories proposed to explain the sudden disappearance of so many large animal species. Theories range from human overhunting to climate change, and even the impact of extraterrestrial objects. The true cause may be a complex interplay of these factors, a perfect storm of environmental and ecological pressures that proved too much for even the most adaptable creatures to overcome. The fossil discoveries at Hunker Creek, and other sites across North America, provide a tantalizing glimpse into the life of camelops. The bones themselves, though often fragmented, tell a story of size and adaptation. More recently, paleogenomic research, the study of ancient DNA extracted from fossils, has shed further light on camelops' evolutionary history. While the genetic material is often degraded, scientists have managed to extract enough DNA to reconstruct partial genomes, revealing details about camelops' phylogeny, or evolutionary relationships, and providing further evidence of its close ties to modern camels. One striking example of the insights gained from paleogenomics comes from the analysis of the ND1 gene in the mitochondrial DNA of various camelids. This gene, involved in energy production within cells, shows a curious difference between Old World camels and their New World relatives. Alpacas, for instance, possess a triplet nucleotide insertion in the ND1 gene that codes for the amino acid proline. This insertion is not found in Old World camels or, importantly, in camelops. This genetic detail suggests that the insertion occurred after the split between the Old and New World camelids, further refining our understanding of their evolutionary divergence. The story of camelops is a tragedy, a tale of a successful species ultimately unable to adapt to a rapidly changing world. But it is also a story of remarkable resilience, a testament to the ability of life to thrive in diverse and challenging environments. The fossils of camelops, scattered across the continent, are not just dry bones. They are a reminder of the dynamic history of life on Earth, and the ongoing interplay between evolution, environment, and extinction. They are a call to understand the forces that shape our planet's biodiversity, and to protect the delicate balance of ecosystems that sustains all life, including our own. Chapter 5. Bridging Continents, the Great Camel Migration. The camel's odyssey across continents is a saga of remarkable resilience, a testament to their adaptability in the face of dramatic environmental change. Their story begins not in the sun-baked deserts of Asia and Africa, but in the unexpected landscapes of North America, a land they roamed for millions of years before embarking on a series of migrations that would reshape their evolutionary destiny. Imagine North America during the Eocene epoch, some 40 to 45 million years ago. A world teeming with ancient camelids, small and unassuming, browsing the lush forests and grasslands. These early camelids were far from the desert specialists we know today. They were creatures of a different world, a North America covered in verdant vegetation, a far cry from the arid landscapes we now associate with camels. As the climate cooled and grasslands expanded, the camelid lineage diversified, giving rise to a variety of forms, each adapted to its specific niche. Among these ancient camelids was Paracamelus, a pivotal species in camel evolution, considered the ancestor of modern-day camels. Around 6 million years ago, during the late Miocene, Paracamelus embarked on a transformative journey, a westward migration across the Bering Land Bridge. The late Miocene was a period of geological and climatic upheaval. The Earth was cooling and ice sheets were expanding, lowering sea levels and exposing the Bering Land Bridge, a temporary land connection between North America and Asia. This bridge, a pathway between continents, provided a route for Paracamelus and other animals to disperse into new territories. The journey across the Bering Land Bridge was no easy feat. The climate was harsh, with long, cold winters and short summers. The vegetation was different from what Paracamelus was accustomed to, consisting of tougher, more fibrous plants. But Paracamelus persevered, adapting to the new conditions, its long legs and broad, padded feet providing sure footing on the varied terrains. As Paracamelus ventured into Asia, it encountered diverse landscapes, from the steppes of Central Asia to the arid deserts of the Middle East. Over time, it diversified, giving rise to two distinct lineages: the Bactrian camel, with its two humps, and the dromedary, with its single hump. The Bactrian camel, adapted to the colder, more extreme climates of Central Asia, developed a thick, shaggy coat for insulation against the harsh winters. Its two humps, substantial fat reserves, provided a crucial energy source during lean times. Its feet, while still broad and padded, became firmer, better suited to the rocky terrains of its mountainous habitat. The dromedary, on the other hand, adapted to the hotter, more arid deserts of the Middle East and Africa. Its coat became shorter and sleeker, reflecting the intense desert sun. Its single hump, though still a substantial fat store, was proportionally smaller than the Bactrian's two humps, reflecting the slightly smaller overall size of the dromedary. Its feet retained the broad, padded structure of its ancestors, ideal for traversing the shifting sands of its desert home. Both the Bactrian and the dromedary developed a suite of adaptations for desert survival. Their kidneys became highly efficient at conserving water, concentrating urine and producing dry feces. Their red blood cells evolved an oval shape, allowing for efficient blood flow even during periods of dehydration. They developed long eyelashes and closable nostrils to protect their eyes and respiratory system from blowing sand and dust. Their ability to tolerate fluctuations in body temperature and to metabolize fat for both energy and metabolic water further enhanced their desert resilience. As the Old World camels diversified, they spread across vast regions, their distribution reflecting their adaptability and their importance to human societies. Bactrian camels became integral to the nomadic cultures of Central Asia, their strength and endurance making them invaluable pack animals. Dromedaries spread across the Middle East, North Africa, and even into parts of South Asia, their ability to traverse vast deserts making them essential for trade and transportation. The diversification of Old World camels also led to the development of various breeds, each with its own unique characteristics. Some breeds were selected for their milk production, others for their meat or wool, and still others for their speed and endurance in racing. This selective breeding, driven by human needs and preferences, further shaped the evolution of these remarkable animals. While camels flourished in Asia and Africa, their North American ancestors met a different fate. Despite their long history and remarkable adaptability, they vanished from the continent around 13,000 years ago, during the Pleistocene extinctions. The exact reasons for their extinction remain a mystery, but several factors likely played a role. The end of the Pleistocene epoch was a period of rapid climate change. As glaciers retreated and temperatures rose, the environments that North American camels had adapted to began to disappear. Competition from newly arrived species, as well as the arrival of humans and their hunting practices, may have also contributed to their decline. Around the same time that Paracamelus crossed the Bering Land Bridge, another camelid migration was underway, this time southward. The Isthmus of Panama, a land bridge connecting North and South America, had begun to form, providing a pathway for camelids and other animals to disperse into new territories. The timing of the isthmus formation is still debated, but it's thought to have occurred between 3 and 2.7 million years ago. The camelids that crossed the Isthmus of Panama found themselves in a diverse new world, a South America teeming with unique flora and fauna. Over time, they diversified, adapting to the varied landscapes of their new home, from the high-altitude plains of the Andes to the arid deserts of Patagonia. This diversification led to the evolution of the New World: camelids, llamas, alpacas, guanacos, and vicuñas, each uniquely adapted to its specific environment. Llamas and alpacas were domesticated by humans, becoming integral to Andean cultures, while guanacos and vicuñas remained wild, roaming the mountains and plains. The story of the camel migration is a testament to the power of adaptation and the interconnectedness of life on Earth. From their North American origins, camels spread across continents, diversifying and evolving to become integral parts of diverse ecosystems. Their journey is a reminder of the dynamic nature of our planet's history, and the remarkable resilience of life in the face of change. Chapter 6. The Camel's Secret Weapon: Surviving Extremes Through Evolution. The camel, a creature synonymous with desert survival, is a testament to the power of evolution. Its remarkable ability to thrive in extreme environments, from the scorching Sahara to the frigid Gobi, is not the result of a single miraculous adaptation, but rather a carefully orchestrated suite of physiological and behavioral modifications, honed over millions of years. These adaptations, interwoven and interdependent, have transformed the camel from its forest-dwelling ancestors into the ultimate desert survivor, a true marvel of natural selection. Central to the camel's survival strategy are its distinctive humps. These prominent features, far from being water storage tanks as commonly believed, are actually reservoirs of fatty tissue, nature's ingenious solution to the challenges of food scarcity in the desert. When food is abundant, camels readily overeat, storing the excess energy as fat in their humps. A single-humped dromedary can store up to 80 pounds of fat, while the double-humped Bactrian camel can amass even greater reserves. This fat, however, is not simply inert storage. It's a dynamic energy source, a biological battery that can be drawn upon when food is scarce. Through the intricate process of fat metabolism, the camel converts this stored fat into not only energy but also metabolic water, a critical byproduct of this biochemical transformation. For every 100 grams of fat metabolized, a camel can produce approximately 107 grams of water. As the fat reserves dwindle, the hump, once full and erect, gradually shrinks, becoming flaccid and even drooping to the side, a visible indicator of the camel's nutritional state. This ability to produce metabolic water is just one element of the camel's intricate water conservation system. Camels are masters of water retention, capable of withstanding levels of dehydration that would prove fatal for most mammals. In the scorching heat of the desert, a dromedary can drink as infrequently as once every 10 days, a testament to its remarkable ability to minimize water loss. They can tolerate a staggering 30% loss of body mass due to dehydration, a feat that would cause circulatory failure in most other mammals. Their kidneys play a crucial role in this water conservation effort, concentrating urine to a thick, syrup-like consistency, minimizing the amount of water lost through excretion. Their feces, too, are exceptionally dry, so much so that desert nomads often use them as fuel for fires. Further enhancing their water conservation is a unique nasal adaptation. The camel's nasal passages are lined with a complex network of blood vessels and mucous membranes that act as a highly efficient dehumidifier. As the camel exhales, warm, moisture-laden air passes over these cool surfaces. The water vapor condenses, and a significant portion is reabsorbed into the body, preventing its loss to the dry desert air. This nasal recycling system, combined with the camel's ability to tolerate fluctuations in body temperature, allows it to conserve precious water, extending its survival in the arid desert environment. Temperature regulation is another key element of the camel's desert survival strategy. Camels possess an extraordinary tolerance for high body temperatures, a crucial adaptation for life in the desert heat. Their body temperature fluctuates throughout the day, rising as high as 40 degrees Celsius, 104 degrees Fahrenheit, in the afternoon sun and dropping to 34 degrees Celsius, 93 degrees Fahrenheit, in the cool of the night. This fluctuation, a remarkable 6 degrees Celsius range, minimizes the temperature difference between the camel and its environment, reducing heat gain and the need for evaporative cooling through sweating. The camel's thick coat, while seemingly counterintuitive in a hot environment, plays a crucial role in this temperature regulation. It acts as insulation, reducing the amount of heat absorbed from the scorching desert sun and minimizing the need for sweating. A shorn camel, deprived of this natural insulation, must sweat 50% more to avoid overheating. The coat also provides protection from the intense ultraviolet radiation of the desert sun and helps to regulate body temperature during cooler desert nights. Dromedaries have an additional thermoregulatory adaptation, a pad of thick tissue over the sternum called the pedestal. When the animal lies down, this pedestal raises its body slightly off the hot desert sand, allowing cooling air to circulate underneath. The harsh desert environment also presents dietary challenges, but the camel has evolved specialized adaptations to overcome these obstacles. The ability to consume thorny plants, a food source most other herbivores avoid, is crucial for survival in the resource-scarce desert. Camels achieve this thanks to a thick, leathery lining inside their mouths and lips, a protective barrier against the sharp thorns. Their split upper lip, with two independently mobile sections, allows them to graze close to the ground, maximizing their intake of sparse vegetation. Inside their mouths, firm, fleshy protrusions called papillae help them manipulate and swallow thorny food without injury. Like true ruminants, camels also chew cud, regurgitating partially digested food and chewing it again to further break down the tough plant fibers. Navigating the sandy terrain presents further challenges, but the camel's unique gait and specialized feet provide effective solutions. Their pacing gait, with both legs on one side moving together, is not only efficient for traversing soft sand but also minimizes energy expenditure during long journeys. Their wide, flat feet, padded on the underside, distribute their weight evenly, preventing them from sinking into the loose sand. Dromedaries, in particular, have a soft, wide-spreading pad on their feet that is specifically adapted for walking on sand, while Bactrian camels have a firmer foot better suited to the rocky terrains of Central Asia. The camel's remarkable resilience extends beyond its ability to conserve water and regulate temperature. Its oval-shaped red blood cells, unique among mammals, contribute to its survival in several ways. This unusual shape facilitates blood flow even during dehydration, when blood viscosity increases. Furthermore, these oval cells can withstand dramatic changes in osmotic pressure, expanding to accommodate large influxes of water without rupturing. This flexibility is essential for camels, allowing them to rehydrate rapidly after a period of dehydration, absorbing over 100 liters of water in just a matter of minutes. The camel's physiological adaptations also include specialized structures that protect its senses. Long eyelashes and bushy eyebrows shield their large, sensitive eyes from blowing sand and dust. The nictitating membrane, a thin, translucent third eyelid, acts like a windscreen wiper, sweeping away any debris that does enter the eye. Closable nostrils prevent sand and dust from entering the respiratory system, protecting delicate lung tissues. Internally, the camel's body is equally well equipped for desert life. A highly efficient circulatory system, featuring a specialized network of arteries and veins called the rete mirabile, plays a crucial role in maintaining brain temperature within safe limits. Located near the base of the brain, the rete mirabile uses countercurrent blood flow to cool the blood flowing to the brain, preventing overheating during periods of high body temperature. The camel's kidneys and intestines are also highly efficient at reabsorbing water. The kidneys have a unique cortex to medulla ratio of 1:4, meaning the medullary part, responsible for concentrating urine, is proportionally larger than in other mammals. This, along with smaller renal corpuscles, which reduce the surface area for filtration, allows camels to conserve water and limit urine volume. The intestines also play a vital role, efficiently reabsorbing water from digested food, maximizing water retention. Camels lose only about 1.3 liters of fluid per day, significantly less than other livestock, which can lose 20 to 40 liters per day. The camel's evolutionary journey is a story of adaptation and survival, a testament to the power of natural selection. From its ancient North American origins to its modern-day success in the deserts of Asia and Africa, the camel has faced and overcome countless environmental challenges. Its unique adaptations, interwoven and interdependent, have allowed it to conquer some of the harshest environments on Earth, making it a true icon of resilience and a symbol of life's remarkable ability to thrive in a world of extremes. The camel's evolutionary journey is a remarkable tale of adaptation and resilience, spanning millions of years and traversing continents. From their unexpected origins in the lush forests of North America to their current reign in the world's harshest deserts, camels have undergone a series of dramatic transformations, driven by environmental pressures and natural selection. Their story challenges our preconceived notions and reveals the dynamic interplay between evolution and environment. Key to this narrative is the camel's remarkable suite of adaptations for desert survival. Their humps, far from storing water, serve as reservoirs of fat, providing energy and metabolic water during periods of scarcity. Their highly efficient kidneys, specialized red blood cells, and unique nasal passages further enhance their water conservation abilities. Their thick coats, while seemingly counterintuitive in a hot environment, provide insulation and minimize the need for water loss through sweating. Even their feet, gait, and dietary adaptations reflect their mastery of the desert environment. The discovery of high Arctic camel fossils challenges our understanding of camel evolution, suggesting that some of their iconic adaptations, such as fat storage and broad feet, may have initially evolved for survival in cold, rather than hot, environments. This finding underscores the dynamic nature of evolution, highlighting how adaptations can be repurposed and refined over time to suit changing environmental conditions. The camel's migration across continents, first across the Bering Land Bridge to Asia and Africa, and later south across the Isthmus of Panama to South America, further showcases their adaptability. This dispersal led to the diversification of the camelid family, resulting in the remarkable variety we see today, from the one-humped dromedary and two-humped Bactrian camel to the smaller, fleece-covered llamas, alpacas, guanacos, and vicuñas of the Andes. The extinction of North American camels, including the giant camelops, serves as a poignant reminder of the fragility of life and the constant flux of our planet's ecosystems. While human hunting may have played a role, the dramatic climate changes at the end of the Pleistocene epoch likely contributed to their demise. Understanding the camel's evolutionary journey provides valuable insights into the broader principles of adaptation, migration, and extinction. It highlights the power of natural selection to shape life in response to environmental pressures and underscores the interconnectedness of species and ecosystems across the globe. These insights can inform conservation efforts, helping us to protect endangered species and manage ecosystems in a changing world. The camel's story also has potential implications for understanding how animals might adapt to future climate change scenarios. What are your thoughts on the camel's remarkable journey? What other animals have undergone similar evolutionary transformations? Share your questions and comments below. If you enjoyed this exploration, please like and subscribe for more fascinating journeys into the natural world. Don't forget to suggest topics for future videos. Never stop learning and exploring the wonders of our planet. The more we understand the natural world, the better equipped we are to appreciate and protect it.